The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So last time we talked about what corresponding to a fundamental, to external fundamental quark in n equals 4 super Yang-Mills theory. So the way we did this was by so you consider n plus 1 these three brane, then you separate one of them. You separate one of them, and then you consider one string connect between. Then you consider the open string connect between this n and this 1. And such an object, from the point of view, because this end have a unique index, and this end have indices, so this will transform on the fundamental representation of this SUM, because when you're reshuffling, the indices of this n, and this will transform as a vector because there's only one end ending on it. So this is the field theory picture. Then in the gravity picture, when you go to ADS, so when you take the low energy limit in the gravity side, then this n brane just disappeared. This n brane disappeared, and then you have a boundary, say r equal to infinity or z equal to 0, and then you find in a suitable low energy limit that the single brane still remains there. And then this string becomes a string just ending on this brane, but extend all the way to r equal to infinity, 0. Okay, because now the n these three brane not disappear, they're replaced by the geometry. So now what you find in that in the gravity side, this just become a single d brane, single d3 brane, lying in the ADS5. Okay, lying in the ADS5, and with 1 point on the S5. So it depends on the direction. So this will be extended in some direction, in the transverse direction to the d3 brane. And so that direction determines the point on the S5. So we are lying on the single point on the S5, and all the three dimension and all the spatial dimension is parallel to the boundary direction. Okay, so this is the geometry clear? Good. And now if we want to consider external quark which have infinite mass, then you want to put this brane to the boundary, because the mass of this quark is controlled by the length. So you want this length go to infinity, then you put it to the boundary, and yeah, essentially. So that tells you that so this picture tells you that the external quark in n equal to 4 super Yang-Mills theory, then is mapped to a string ending on the boundary. Okay? A string ending on the boundary. Do you have any questions regarding this picture? And the mass of the string, as we discussed before, either from this picture, the mass of the string would be the length divided by 2 pi alpha prime. And this mass gets inherited to this picture. And then you can check it as a self-consistency check that the straight string extends all the way, say from some radius, from some location r to the r equal to 0, and precisely have this mass. Okay? So now let me make a note. So as we said before, if you say in the ordinary gauge theory, if you take external quark, say moving in the fundamental representation, and when you parallel transport that quark, say along some loop, then you get the Wilson loop. Okay? Then you get the Wilson loop. But in this case, the parallel transport of this quark of such an external quark actually gives something which is slightly different from the standard Wilson loop. So the standard Wilson loop is the following. Is that you take the trace, you pass order, and the exponential, say I, a mu, suppose S parameterize the length along the path, and then you have a mu, then you have dx mu, ds. Okay, so this is the standard Wilson loop. But in this case, actually, you have something more in the exponential for the following reason. So if you think, so in the equity for super Yang-Mills theory, you not only have a gauge field, you also have a scalar field. And the scalar field essentially parameterizes, as we said before, the scalar field parameterizes the external, the fluctuation in the external, in the transverse direction of the d branes. Okay. So now, if you imagine you have a string ending on such d branes, just by mechanical thinking, really mechanical thinking, if you have something ending on the d brane, and if this thing have a mass, and it got to pull this d brane, okay, in the direction, because this thing have a finite tension, so you want to pull the d brane. So that means that the string actually will deform the shape of the d brane around the ending point. So what that means is that the string should couple to the scalar field on the d brane. Okay, such an open string should couple to the scalar field on the d brane. The scalar field parameterizes the transverse direction, the transverse motion, and the string should pull the d brane. So this d brane got to couple to the so this open string got to couple to the scalar field. Okay, so this is a rough intuition, but you can work out this out explicitly. You just take this theory. So this is SUN Yang-Mills theory, n plus 1 Yang-Mills theory, and then you break to SUN times U1. So this open string corresponding to the off-diagonal degrees freedom when you do this breaking between the n and the 1, and corresponding to an explicit field in this theory. And you can just work out the dynamics of that field. You can easily check that actually this coupled to that scalar field. So I will not go into detail there, but you can work out very explicitly. Okay. So the bottom line is that such a object will not only couple to the gauge field, but also couple to the scalar field. And if you work it out explicitly, it coupled to the scalar field in the following way. So let me just. So let me denote the phi. So you have 6 scalar fields. Let me denote them as a vector. Okay. Yeah. So now let me explain this notation. So this n is essentially the direction of the string. So this will. So n is a unit vector on S5, which is the location of that d brane, okay, which is labeled the location of this d brane S5 because it's in some transverse direction, okay. And the phi is just the 6 scalar fields, which I write the vector 6 fields of n equal to super Yang-Mills theory. Okay. And then dot x squared is just the modulus of this guy. Okay. Do you have any questions on this? So now, because this is the Wilson loop corresponding to such a string, such a external quark, and then naturally, when we consider the string dynamics on the gravity side, that will relate to the expectation value, for example, of this Wilson loop. Okay, not the standard one. Okay, so now let's consider such a quark traverses some path C, some loop C on the boundary. Okay. So we'll make two statements, and from these two statements, then we will be able to guess what the Wilson loop will correspond to on the gravity side. Okay. So the first statement is that this quark lies at the end point of a string in a DS. Okay. So that means the C, so the loop formed by this quark trajectory, there must be the boundary of the corresponding string worldsheet. Okay, so let me call this worldsheet sigma. Okay, so in other words, the C must be corresponding to the boundary of the sigma. Okay. So the second statement is that the Wilson loop, the expectation value of the Wilson loop, so this can be considered as the partition function of this quark system. Okay. So you can think about the expectation value of the Wilson loop as the following. So you take the quark and write down the path integral for this quark along. Write down the path of the quark along this loop, and then just integrate all possible. Just integrate over the dynamics of the quark, and then what you remaining would be just the it's this Wilson loop. Okay, so you can just imagine this Wilson loop corresponding to the partition function of this quark system. So now, from our experience with string theory, with the duality, now we can just make a guess. We can just make a guess because we always identify one partition function with the other partition function. They should be the same object. So now we should be able to identify the expectation value of the Wilson loop with the string partition function of this particular string, which ending at the boundary, the string partition function, and whose worldsheets ending at the boundary as at C. Okay. So this is just you can just make a natural guess. Do you have any questions regarding this guess? Good. So now let me say a few words about this guy. Okay. So suppose let's just parameterize, say x, say m, sigma alpha to parameterize the worldsheet. Say sigma alpha is the worldsheet coordinates, and xm are the coordinates on the ADS, in the ADS. And then this parameterizes a stream moving in ADS. And then the stream partition function, you can just write it as dx. You integrate over all possible x, and then the string action with the boundary condition that the worldsheet of the boundary should end on C. Okay. So this essentially is the right-hand side. So according to your convenience, you can either choose the string action, say to be Lamborghini or Polyakov, as you want, okay, or Polyakov. For example, let me just write down remind you what is the Lamborghini. For the Lamborghini, you just 2 pi alpha prime letter h, and the h is the induced metric on the worldsheet. Okay, h is the induced metric on the worldsheet. Yeah, so now we have a precise, so in principle we have a precise mathematical formulation we can work with. Then you can check whether this proposal makes sense, etc. Okay? Of course, again, this object is very hard to calculate. Yeah, I should say you may also include the fermions, depending on the superstring, etc. You may have other things, but this is the most basic object. Okay. So again, these objects are in principle very difficult to calculate, but then become simple if we consider the G string goes to 0 limit, and the alpha prime goes to 0 limit. Okay. So in the G string goes to 0 limit, you remember then we can neglect different topologies. You can just stick to the lowest topology. So in other words, you can when G string goes to 0, you can neglect splitting of the string, splitting or joining of the string. Okay. So you can just consider the worldsheet with the simplest topology. And in alpha prime goes to 0 limit, so alpha prime appears as a prefactor. 1 over alpha prime appears as a prefactor in this worldsheet theory. Whether you do the Polyakov or you do the Lamborghini, it's the same thing. So alpha prime essentially places the coupling constant on the worldsheet. Okay. So the alpha prime goes to 0 limit. So alpha prime is essentially the h bar on the worldsheet. It's the effective h bar on the worldsheet. Okay. So when the alpha prime goes to 0, you can evaluate then the path integral. Just like in the gravity formulation, we can evaluate the path integral when the G Newton goes to 0. So here we can evaluate path integral using the saddle point approximation. Using the saddle point. Okay? So this means, so this is equivalently implies using the saddle point expression, essentially you just evaluate the classical action. Okay, just find the classical solution, classical string solution, and then evaluate the action on that classical solution. And so this is corresponding to neglecting fluctuation of the worldsheet. Okay. So as I said, this alpha prime appears in the worldsheet action just as the place which is, the h bar appears. And so when you take alpha prime goes to zero limit, then corresponding to you neglect the fluctuation of the worldsheet. Then you can just consider the classical string dynamics. Okay. Then in this limit, then we can do this easily. So that means in the G string goes to zero limit, and the alpha prime goes to zero limit, which again translate on the field series side to the n equal to infinity, and the lambda goes to infinity limit. Then we can write the expectation value of the Wilson loop just as the classical action, the action for the string evaluated as the classical solution. Okay. So SCL is the action evaluated at a classical solution. So essentially, you just have a rigid worldsheet. Any questions on this? So now we can talk about some examples. So the simplest example is that let's just consider a static quark. Okay, a static quark does not move. So if this is the time direction, then the word line of the quark is just a straight line moving in the time direction. Okay? And say from minus infinity to plus infinity, and then you can imagine close the loop at infinity. Yeah, anyway, this is just a straight line. Okay, so this is a simple situation. And so let me, levelers is convenient to give a length to this line in the time direction. So they will call the total length is t, capital T. Okay? And then without calculating, then essentially by definition, the expectation value of the Wilson loop should be just minus IMT. Okay, so this is just the this is the phase factor associated with transport this thing, and the quark does not move, and the m is the total energy of the quark, the mass of the quark, and then you just have the standard minus IET. Okay. So now let's try to calculate on the gravity side. Okay. Now let's try to calculate what is the corresponding object to this on the gravity side. So I will use the, so now let me just remind you the ADS metric. So we can use the two different ways, say whether using this r coordinate or using these z coordinates, and they are related by a very simple coordinate transformation. Okay, just 1 over, remind you that. So on the gravity side, so let's now draw our boundary. So this is I equal to infinity or z equal to 0. Okay, so the r increase in this direction and the z increase in that direction. Okay. So such an object on the gravity side, just from the description we said earlier, would just corresponding to a string does not move at all. It extends from the boundary all the way to the interior. Okay? And because this is just a single quark does not move, this is just our previous picture. Okay? So let's just, we can parameterize it. So as we discussed before, this action is parameterization, reparameterization invariant. So that means you can choose the sigma and the tau at these 2 sigma coordinates, so sigma alpha. I will call the tau and the sigma. So I can choose the tau and the sigma as we want, according to the convenience. So for this one, let me choose tau equal just t at the real space-time t, so that t, and then take the sigma along the radial direction, that's r. Okay. So this straight string just corresponding to the solution which xi tr equal to constant. So this is a string which does not move. So the other directions, it's just a constant. If you put it at some point, it stays there. Okay. So this is the obvious solution of that configuration. So you can check this is indeed the solution to the Lamborghini action. I will not check there because this is the essentially all started with. So you can immediately tell this must be a solution. Okay. So now let's try to find the classical action corresponding to this solution. So for this purpose, we have to work out this induced metric. So the easiest way to work out this reduced metric is as follows. So the worldsheet metric would be H alpha beta, say d sigma alpha, d sigma beta. Okay, and H alpha beta is given by this guy. Okay. And the easiest way to work out is that you just write down the ADS metric. And now you think each t and x and r as a function of this sigma and tau, and you just substitute that functions in. Okay. So t just equal to tau, so this just becomes d tau square. But x is independent of t and r. So when I write the space-time coordinate, I use x. But then when I write that coordinate as a function of the worldsheet, then I use the capital. So this is the just to emphasize this is a function. Anyway, and here I replace by that x, which is independent of xt, so there's nothing here. And now the r square becomes sigma square. So it becomes sigma square because r is just equal to sigma. And then this is my worldsheet matrix: sigma square, r square, minus d tau square plus r square, sigma square, d tau square, d sigma square. Okay. So this is my induced worldsheet metric for this special worldsheet. And you should imagine there's a time direction, which this string just translate in the time direction. That's not moving. Okay? So now we can easily work out what is the determinant. This is diagonal metric. You see these two cancel. So the determinant is just equal to 1. Okay? So now we can write down the worldsheet action. Maybe erase here. So the worldsheet action SNG would be just minus 1 over 2 pi alpha prime. Now the delta H is just equal to 1. Then I just have integration over dt. Then I have integration over dr. Because tau equal to t and the sigma equal to r. Okay? And r should be from 0 to infinity. So this integration of dt just gives us a capital T factor. And this is divergent. Okay? So normally when we see something divergent, as we always do, we just say this is not at infinity. Let's put a small cutoff here at r equal to lambda. Okay? So if I do that, and then this just becomes lambda. Okay? So now if you read from here, this should be identified with WC. I times of that object should be identified with WC, and that should be equal to minus IMT. So we conclude that the mass must be lambda over 2 pi alpha prime. Okay? But this is actually what I just advertised earlier, so that you can check it explicitly, that the mass of the object is precisely just the radial location divided by r, divided by 2 pi alpha prime. Okay? And I just confirmed that expectation. Okay? I just confirmed that expectation. So, and this is infinite by design, because I want to have an infinite mass quark so that I don't have fluctuation. Okay? And so in principle, I can take lambda as large as I want, but actually I can control the lambda. So it actually makes sense. So physically, you should think there's some kind of D3 brane here which I can control the location. And in the end, I take lambda go to infinity because I want the mass to go to infinity. Okay? So it's also instructive to rewrite this in terms of the z. So in terms of the z, and the z is related to capital R by this way, then this corresponding to a small thing in z. So z will be r squared. So this corresponding to a cutoff z at epsilon. Okay? And epsilon. So we can write this m in terms of z, then equal to become 2 pi alpha prime r squared divided by epsilon. So now let me do one more step. So as we said before, that in terms of z coordinate, so you also have checked yourself by doing this holographic bound, etc. So this epsilon can be considered as a short distance cutoff. Because of the boundary. Okay, short distance cutoff boundary. So this can also be considered as the mass of the quark, and due to that you put some short distance cutoff, say epsilon distance away from the quark. Okay. And so now let's remember the dictionary. R squared divided by alpha prime is related to, on the gravity side, to what? Do you remember? Yeah, let me write the big box here. So r to the power 4 divided by alpha prime square equal to what? Equal to lambda, which is the g on mu square n. Which is g on mu square n. And then the 5-dimensional Newton constant divided by r cubed, that is related to the n. So this is, I think, it's pi divided by 2n squared. Okay? You don't need to remember the precise prefactors, but you should remember that r squared divided by alpha prime is related to lambda. Okay? So lambda is the Hooft coupling. So now we can rewrite this as a square root lambda divided by 2 pi, then 1 over epsilon. So there's something interesting here. He said there's a square root lambda. Okay, it's a square root lambda appearing here. And this is a square root g squared times n. So if you remember in the QED, so if you try to calculate what is the self-energy of the electron in the most naive way, so the electron naively have infinite potential energy, because if you go closer to the electron, and then the energy will blow up. But if you put a small cutoff around the electron, then what would the energy you get? Yeah. Say if you put 2 electrons, you use a lot of electrons to probe it. Then you would get E squared. Okay, you would get E squared. But here, interesting thing is that it's proportional to the square root of the E squared. Okay, this is proportional to the square root of the square. So this square root lambda is essentially the strong coupling prediction. We will say more about this. Okay. Okay, so we have finished this simple example. Seems to make sense. Okay, so this is just corresponding to a mass of the quark. So now let's do something a bit non-trivial, a little bit more non-trivial. So let's consider the static potential between a quark and the anti-quark. Okay? So from the field theory side, we consider such a configuration. So suppose this is some x1 direction. So this is the time direction. So we consider such a loop. So this is L in the x1 direction. Say this is L divided by 2, and this is minus L divided by 2. And in the t direction, again, the length is capital T. Okay, the length is capital T. And we always take the t to be much, much greater than L. Okay, essentially, you can imagine this t is infinite. Okay. So as we mentioned last time, this is a if you can see the loop like this, when the t becomes much, much greater than L, you can forget about the beginning part and the end part. Essentially, you have two parallel lines. And two parallel line runs in the opposite direction in time. Then you can consider this is corresponding to a quark, this corresponding to the anti-quark, moving parallel in time. And then this, again, the expectation value of the Wilson loop should give you. So this is a static system. Okay. This is a system with translation invariant in time. If I take t go to infinite, okay, you can imagine as a translation invariant in time, and then this, due to its translation invariant in time, you can write it to leading order in large T. It must have the following form, just on general ground. And E total is just the total energy of the system. Okay, just in quantum mechanics. In quantum mechanics, any translation invariant system, the whole thing just minus IET. Okay, and the E total should correspond to the mass of the two external quarks, then plus the potential energy between them. Corresponding to the potential energy between them. Okay. So if you calculate this Wilson loop in say in QCD, so that will give you the force between the quark and the anti-quark, etc. But in general, if you have a strongly coupled gauge theory, we don't know how to do such a calculation. Okay, it's very hard to do. But in this case, equipped with this, equipped by this, then the gravity will help us to do this calculation. The gravity can help us find VL and strong coupling. Okay. So now we want to calculate the string worldsheets corresponding to such a configuration. Do you have any questions regarding our setup? Okay, good. So now let's write, consider the gravity side. Again, this is the boundary of ADS. And now let's imagine this is our x1 direction. Then we have a quark here at L divided by 2, and then have anti-quark here at minus L divided by 2. Okay? So you consider these two lines as one from quark, one from anti-quark. And now this is translates in time. Okay? So if you, so this is the r equal to infinity, or z equal to 0. So if we just have two isolated quarks, if each of them are isolated, then the string worldsheet will just, as we said before, just two straight lines. Okay, just two straight lines. And that's corresponding to an isolated quark. But now, these two quarks can interact. Okay? Can interact. So the natural expectation is that this string worldsheet will get deformed, and the natural expectation is that they will just connect to each other. Okay. So you expect the string worldsheet will be like this. So if the string worldsheet is like this, that means there's no interaction between these two quarks. Okay. And now, if the two string, so this is the quark, and this is the anti-quark, so they should have all opposite orientation, and then the string worldsheet will have orientation like this. So we'll go off like that. So now you expect that the worldsheet will be like this. Okay? And again, it's translation invariant in time. Any questions on this? Is this clear to you? So geometrically, this is the only way which these two quarks can have interactions. It's by joining their worldsheet together.
So generally, you'd be doing the path integral over all closed strings that have those boundary conditions. Sorry, open string.
Yeah, that's right. That's right, yeah. Good? Okay. So now, with this realization, then the rest become mechanical. Not quite mechanical, with a little bit, yeah, so we can choose, as before, tau equal to t. So t equal to infinity. So we can consider the system translation invariant in time. Okay. So let's choose, again, tau equal to t. So we can also choose the sigma still equal to r. But now let me do it slightly differently. So let me do sigma equal to x1. So you can do both, but just to give you a variety, let me not choose sigma equal to x1, because x1 direction also become non-trivial. Okay, let me choose sigma equal to x1. And then this worldsheet then is parameterized just by z, which is only a function of sigma. Okay, so sigma runs from minus half L to L, and z, then this string will be parameterized by some function of z as a function of sigma. And because of the translation invariance, you cannot have dependence on t. Okay, cannot have dependence on t. And also all the other directions I not equal to 1, they should be just constant. Because they're not moving in the other directions, so they should be just constant. Okay, so the only non-trivial thing will be in the x1 direction. You can also choose the sigma to be z, and then the x1 then will be a function of z. Then the x1 will be a function of sigma. You can do it either way, doesn't matter. Okay, so the boundary condition would be z when you evaluate it at plus minus 1/2 L. Then this, of course, should be at the boundary, so it should be equal to 0. So this is the boundary condition that this starting from the boundary. Okay. So now let's try to write down the worldsheet action. Okay, let's try to write down the worldsheet metric. Yeah, under the worldsheet action. So the worldsheet metric is again as what we were doing before. You can just write down I equal to z square minus dt square plus dx square plus dz square. Okay, so now t equal to tau. So dt square just becomes d tau square. And the dx1 square just becomes d sigma square, and the others we don't need to care, so this just becomes d sigma square. And the z is a function of sigma, so this just becomes z prime sigma square d sigma square. Okay? And then you just find this is equal to r square z square d tau square plus 1 plus z prime square d sigma square. Okay? So this is the induced metric on the worldsheet. And then you can now write down the Lamborghini action. So it's just 1 over 2 pi alpha prime d2 sigma. And then you take the determinant of this metric, which is easy to do. You get the r square factor out. And then you get 1 over z square. And then just square root 1 plus z prime square. Okay, so this is the square root determinant. Okay? So we can do a little bit massage. So this d2 sigma is dt d sigma, and sigma is from minus L to 1/2 L, because this is the sigma is x1 from minus L to 1/2 L. Okay. So first, nothing depends on t, so we can just replace it by a factor of capital T. Okay. And obviously, this system will have symmetry between the x and the minus x. Okay. And then I can just choose the integration from half of it. I do it from 0 to L divided by 2. And then I eliminate the 2 on the downstairs. Okay? So this is my action. Then what I need to do is I need to extremize this is action with respect to this sigma. Then you solve for this sigma, which satisfies the boundary condition, and then solve for this sigma, and then find S classical action. Okay. So now this reduced to a freshman problem, literally little cute freshman problem. So which is actually quite fun to do, with a little bit twist. So do you want to do it immediately, or do you want to have a break? Okay, so now let's try to do this. So first, we expect, just by consistency, we expect this thing must be divergent, okay? Because this contains 2m, but 2m in our setup, if you start something from the boundary and the m is infinite, and then we would expect this thing to be divergent, okay? We would expect something to be divergent. And indeed, you see the dangerous thing is that when the sigma approach L over 2, then you have a 1 over d squared here. And at z of 1 over 2, L over 2, this is 0. So there is some potential divergences here. Okay, but of course, we also have to look at the behavior of this term. But at least you see there is some potential divergence here. And this is expected because we know that this must contain the 2m. And if this whole story is consistent, there must be a divergent. Okay? So let us just write with that in mind. So let me just subtract the 2mt from here. So this ENG, so this is supposed to be minus I E total T, okay? So from this expectation, we would write VL. So now again, I replace the R squared divided by alpha prime by square root lambda. So I will have square root lambda pi, then L divided by 2 d sigma 1 over z squared 1 plus z prime squared, and the minus now 1 over epsilon. Okay? Because twice the m is just the square root pi divided by square root lambda divided by pi times 1 over epsilon. Okay, so I take out this factor. And so we expect the VL just given by that. So if this guess we have said earlier is correct, that the partition function of the Wilson loop should be related to the partition function of the string, and then reduce to a classical action, etc. If that idea is right, then we should find by self-consistency that this thing should be finite. Okay, this thing should be finite, and should also be negative, because the quark and anti-quark have attractive force. So we should find this thing to be finite and negative. You see, this guy is actually positive. No matter what is z, this guy is actually positive. So that means that this guy must be smaller than 1 over epsilon. And so you get something negative, okay? So this guy must be some 1 over epsilon minus something. Okay, so now let me call this to be my Lagrangian. So now we have to do a small variational problem. Yeah. Let me not confused by that L. Let me call this script L. So this is my Lagrangian, and so I can choose. And this is a one-dimensional Lagrangian problem, and this Lagrangian does not depend on sigma. Okay. So if the Lagrangian and we treat the sigma as time, so this is like a one-dimensional problem with the sigma as time. So if the Lagrangian does not depend on time, what's going to happen? Exactly, the energy is conserved. Energy is conserved. So we can write down the energy corresponding to this guy. Then the energy is z prime pi z minus L. So this must be constant. And the pi z is just the canonical momentum conjugate to the z. Okay. So all this is very elementary. You can immediately write down this equation. This is 1 over d squared. Okay, so you find the pi, you plug it here, then you find this equation. This equation just becomes that. Okay. So now let's try to parameterize this constant. So the way to do it is just look for the special point on the trajectory. So the special point on the trajectory is this point. By symmetry, it should correspond to sigma equal to 0. So this point should correspond to sigma equal to 0. And so let me call this point z0. So this is essentially how deep this string going into the bark. So let's call that to be z0. So it's clear at sigma equal to 0, the z prime should be z equal to 0. So I can just call this. So this should be just equal to 1 over z0 squared. Okay? Should be 1 over z0 squared. And then you can just immediately rewrite this as ordinary differential equation. So now you can immediately integrate this equation, okay? And say z0 is found, is determined by the boundary condition by requiring zL equal to 0, okay? So I will not do it here, but you can do it in 30 seconds to find the z0. You actually don't need to actually integrate this equation. There's a simple trick to do it. Anyway, so let me just write down the answer. You can find the z0 equal to L. It's proportional to L, and then square root pi divided by 2, gamma 1/4, and gamma 3/4. Okay? Oh, this funny number, yeah.
30 seconds.
Yeah. Yeah, mathematical will tell you. It takes you 25 seconds to type into the Mathematica. and the 4 seconds to check the arrow. And the Mathematica 1 second to give you the answer. Okay, so you find this. So we will comment on its implication a little bit later. So now we can plug this into this action. So let me see. Yeah. So now let me plug this equation back into this equation. Okay. Into star. So there's again a simple trick to do it. You don't need to know the explicit form of z, because what you can do is you can rewrite this VL. You can rewrite this integral as follows: VL, say this square root lambda divided by pi. So this d sigma, you can write it as dz divided by z prime. So this is the d sigma. You can change the variable from sigma to z. And then this just integration becomes z is 0 to z0. And then you have the 1 over z square, 1 plus z prime square. Okay? So now you can substitute what is the z prime into here. And now this just becomes integral over z. And just pure integral. We still need to minus 1 over 7. Huh? Okay? So if you plug into the expression for the z prime, and then do a scaling, say take z equal to z0 y, because you see these all have the nice scaling form, so it's good to scale the z0 out. So so let's do a scaling z equal to z0 y. Then you can rewrite that integral. Sorry, this is not vz, this is vl. So you can rewrite that integral as VL equal to square root of pi, square root lambda divided by pi, 1 over z0. So now I have put the epsilon in here, anticipating that this integral will be divergent here. Okay, so this is the same epsilon we put in there when we do the single quark. The single quark. So we put there. Yeah, maybe let me just write one more step so that you can see it more explicitly. Yeah, so so I just plug this in. Plug this into here. Then what you get, square root lambda, z0 square, epsilon. Then I put the cutoff in the epsilon. Then this becomes dz square. Okay? And now I can do this scaling to express in terms of y. And then this becomes square root lambda pi, 1 over z0. y over 1 over y square. Over 4. So minus 1 over epsilon. For simplicity, I will slightly rewrite this 1 over epsilon into the following thing. Just as a contrast, as from infinity, epsilon divided by z0 dy divided by y square. Okay? You can easily do this integral. This integral, you integrate just 1 over y. And the upper end give you 0, lower end give you z0 divided by epsilon. And then the 0 cancel with the 0. So you just get 1 over epsilon. But the reason to write in this form is to see that these two singularity indeed cancel. So these have a singularity as y goes to 0. This is non-integrable. And here you have the same singularity, they cancel. So when near the y equal to 0, they cancel, and the next order term comes from by expanding this term. Then you get the y to the power 4 when you expand this term. In the upstairs, you get the 1 over y power 4, and then that will give you something finite. Okay? So that just tells you, immediately see the singularity have cancelled. Okay, so you will guarantee to get something finite. Okay, you will guarantee to get something finite. And another reason to write in this form is that this is something integrate to 1, and this is something integrate to infinity. It turns out the difference between them is negative. Okay, because you have to really do the calculation, but this is because integrand is not exactly the same. But the fact that this is going to infinite give you a chance that this becomes negative. And when you calculate it, it's indeed negative. So, and now, literally, you can do it. Yeah. So you can write down the answer. You find the answer is given by something like this. It's minus square root lambda divided by pi, then some numerical factor, which is not very important, but let me just write it down. To the power 4. Okay, so this answer is nice. So then, now let me make some final remarks. So this is finite and negative. Negative. So this passes the minimal consistency check that we are doing something sensible. Okay. We are doing something sensible. If you find something infinite, then that proposal must be wrong. You can immediately root it out. And if you find something positive, then you can also immediately root it out. And so at least this is a self-consistency check. Oh, I forgot the y, 1 over y, z0. Oh, yeah, actually, if you plug in the 1 over z0, I think you just, no, I write it wrong. This is not pi, this is L. So I have already plugged in the z0. So z0 is given by this, is proportional to L, and then this is 1 over L. Okay. So this 1 over L is also makes sense physically, because 1 over L is just the Coulomb potential. And we do expect the Coulomb potential because we have because n equal to 4 super Yang-Mills series, we said is a scale invariant theory. And in 4-dimensional scale invariant theory, a potential just on dimensional ground would be 1 over L, just by scaling symmetry. It's just exactly like y electromagnetism is 1 over L. Okay, and so this is just from the scale invariance. There's no other scale, so the dependence on L must be 1 over L, because V have dimension mass. Because V have dimension mass, they cannot have other L dependence. Okay. So the second point is now we again see this proportional to square root lambda. Again, this is a strong coupling result. Because at weak coupling we know at weak coupling we know it must be proportional to lambda divided by L. Lambda is just the analog of the fine structure constant, and then this is the Coulomb potential. So we see that this potential, so when lambda close to 0, so this prefactor, so 1 over L is always true no matter the value of the coupling. So you see when you dial the coupling from lambda equal to 0, then it should be linear in lambda. Then when lambda goes infinity, then become the square root in lambda. Okay? So now the final remark is that we see that Z0 is proportional to L. So what's the physical? Now let's look at the geometric meaning of this Z0. So this is Z0 is how far a string extends into the bulk. Say if you say L is small, then Z0 is small. Now, if L is large, if I make L large, then the 0 becomes bigger. That means that the string extends further into the bulk. Okay? And when you take L go to infinity, and then this go all the way to the ADS. Okay? And again, this is the reflection of IRUV. Fraction of IRUV. Because the L corresponding to whether you measure UV physics or IR physics in the field theory. So L small is a short distance physics, L large is long distance physics. And you see, when you probe long distance physics, then you are probing much deeper in the interior in ADS. Okay? And if you're looking at short distance, then you're probing the region very close to the boundary. Okay? So any questions on this? Yes?
So are there any like interesting experimental implications of these sorts of things that we couldn't get otherwise? Like could we have known these four facts basically without doing this calculation by using more standard techniques?
You mean this thing?
Yeah.
No.
No.
Yeah.
Interesting.
Yeah. Yeah. So this is really strong coupling prediction.
So what would that correspond? Like what sort of thing could you measure in nature that would sort of?
Yeah. So that's what you would do in your p-set. So in your p-set, in the last problem, you will calculate this thing at the finite temperature, which we will talk about. We will talk finite temperature in a few minutes. You do it in the finite temperature.
Yeah.
And that's precisely, and then you can essentially calculate this potential at the finite temperature. And as you will do in the p-set, there's a screening length. At the finite temperature, is no longer scale invariant. Beyond a certain length, the potential will go to 0. And you can measure the screening length. And people on the lattice QCD, they precisely measure that. So you can compare ADS calculation to the strongly coupled QCD calculation, spend a huge amount of computing time, large amount of money, large amount of manpower on the computer to do that kind of Wilson loop calculation on the computer. And then you see the answer is very similar. Yeah.
It's a simple question, but is it the strong coupling because it's proportional to square root lambda?
Yeah.
But the square root lambda was what you said from the beginning because it's just inversely proportional to alpha prime, and then it does not involve the calculation at all. So this will never produce a weak coupling result.
Oh, sure. Because we are calculating strong coupling. Because we are calculating the strong coupling. Yeah. So this whole setup is for the strong coupling.
So you can't this formalism cannot treat weak coupling.
No, but weak coupling can do Feynman diagrams. You don't need this. Yeah. But strong coupling, we have no other way to do this kind of calculation, other than doing massive computer simulation. Yeah. And for some things, you cannot even do computer calculation. Yeah. Good. Any other questions? Yeah. So this is a good question. So this is actually a very good point. So this tells you on the gravity side, essentially anything involving this is always proportional to square root lambda, just related to 1 over alpha prime. Yeah, it just comes from the kinematics. Yeah, but this is but nevertheless, this is a very non-trivial prediction of the strong coupling behavior. Good. We need to go to the finite temperature because I want you to be able to do your p-set. So now we have talked about various observables. How to calculate the various observables. Now we can pause a little bit to talk about other generalizations. So the first generalization is that let's do finite temperature, to non-zero temperature. Okay. So far we discussed, say, ADS5 times S5, string theory in ADS5 S5, string in ADS5 times S5 is related to invertible Yang-Mills theory. Okay. So we talked about, at least in terms of small perturbations, the normalizable mode on this side should map to, say, some non-trivial state, to some states. State. Say you have some normalizable mode should dual to some states. And for example, the pure ADS5. So with nothing excited, this is an example of this such kind of a normalizable mode. And so this should be dual to the vacuum because nothing excited on the field theory side, so this must be dual to the vacuum. So now start with this pure ADS5. Now you start putting things inside, excite the system, and then you will say, in some sense, excite some normalizable modes, and then you go to excited states in your Yang-Mills theory, okay? And then one of the obvious excited states is the finite temperature state, okay? So the obvious question is, what does the thermal state correspond to? Yeah, corresponding to, just save time. Let me. Okay, so the gravity description should satisfy the following conditions. Should satisfy the following features. So now we want to guess what should be the thing on the gravity side. First, he said it should be a asymptotic ATS5. That means that there should be only normalizable modes. Okay, there should be only normalizable mode because the finite temperature state is a specific state of the field theory. So, so there should be no non-normalizable modes excited. And of course, if the field theory have a finite temperature, the other side must also have a finite temperature. So must have a finite temperature. So now I use T means the temperature. Now the capital T means the temperature. And in particular, this should satisfy all laws of thermodynamics. Okay. And the third one is that you should have, of course, have all the symmetries of the finite temperature system. So you should have translation invariance, the rotational symmetry, etc. Of course, the Lorentz symmetry, Lorentz boost will be broken. So you still should have translation symmetry and the rotational symmetries. But the boost will be broken because now when you add finite temperature, you no longer have the Lorentz boost. Okay? So you need to find some kind of gravity solution which satisfy those criterions. So there are two obvious candidates. So there are two candidates. So the first is just you consider some kind of thermal gas. In ADS. So just imagine you have some thermal gas in ADS. And the second possibility is that you have a black hole. Okay? Because we also know a black hole is a thermal object. Okay, we also know black hole is a thermal object. So it turns out, so we will only consider the Poincare patch. So we only consider the boundaries. Is really the R3 rather than the sphere. So the thermal gas. So let me first describe the thermal gas description. So normally in the field theory, how do you describe a thermal system? So how would you describe a thermal system? In field theory. Yeah, it's a partition function is one observable of a thermal system. So if you want to describe the thermal system in field theory, what do you do? So if you want to calculate correlation functions, you want to calculate many other things. Exactly. So normally in the field theory, what you do is that you go to Euclidean signature, and then periodically identify time, and the period of time is the inverse temperature. Okay. So we can do it here. The thermal gas in ADS essentially is what we do, is that we go to the Euclidean signature, and we take, let me call it TE. We go to Euclidean time, and then we identify Euclidean time periodically with inverse temperature, which we always call beta. And so in particular, the fermions is anti-periodic. Okay, anti-periodic. Okay, fermion is anti-periodic. Of course, the boson is periodic. But actually, this metric is bad for the following reason. So in gravity, as a general rule, whenever you see a compact space go to zero sides, then there's a danger of having a curvature singularity. It's almost always you have a curvature singularity. Only for some special situations it does not happen. And so this is bad because now when you compactify this Euclidean time, this becomes a compact direction. This is a circle. And when you go to z go to infinity, this circle goes to zero sides. Okay, you can check that actually this have a curvature singularity. So this is actually bad. So when T is uncompact, and then this is a coordinate singularity. But when T become compact, and then this becomes a genuine singularity. Okay, this becomes genuine singularity. So first, this metric is bad because it has singularity at z equal to infinity. Okay, at deep in the interior of ADS. There's also a second reason, which is a more stringy reason, which you don't need to care. Let me just write it down for completeness. So if you actually analyze a string theory in such kind of space-time, so also there's a generic rule in string theory. If you have a very small circle, then the string can wind around the circle. Okay, the string can wind around the circle. And when that circle becomes very, very small, then take less and less energy for string to wind around that circle. And normally, so if you have supersymmetry, and also when you have a string wind around circle, there's a Casimir energy. And the Casimir energy typically is negative for the boson, and the fermion is positive. And if you have a supersymmetry, then that Casimir energy cancels. And then when the circle shrinks to zero sides, then the string becomes massless. So that's typically in the superstring. But if you're in the bosonic string, but if you're in the situation which supersymmetry is broken, then typically there's a negative Casimir energy. And when the string side becomes the circle side becomes smaller and smaller, and then take lower energy for string to wrap around the circle, and then the Casimir energy. Yeah. Anyway, if you include the Casimir energy, etc., then you find the string actually become negative energy, and you find that the strings winding around TE actually develops negative mass square. Okay? So as we discussed before, this is called tachyon and signal instability. And here there's a circle which become small size. And here there's no supersymmetry because when you have a finite temperature, your supersymmetry is broken because boson and fermion have have different boundary conditions. Anyway, so that means that this option is gone. It cannot work. So the only thing we know is to do a black hole. Okay? So now we need to find a black hole with the right symmetry. So the reason I emphasize with the right symmetry is because in the standard case, when we say black hole, it's because black hole is a hole. It's a spherical symmetric hole. But here we need to have a translation symmetry because this is a planar. So here now we need to have a black brane. The whole horizon is actually not a hole, it's actually a plane. Okay? So need the black hole with topology. So the horizon topology should be r to the d minus 1 rather than a sphere. Okay? Okay, once you realize that, then it's easy to do. Once you realize that, it's easy to do. So you can just write down answers, because this system have lots of symmetries. And you can just write down answers and then just plug into the Einstein equation to solve it. Say for example, you can write down the answers. So you can write down, say, r squared. So you can write down answers ds squared equal to r squared divided by z squared. So now you still need translation symmetry. So you can put something before dt squared, but you still have rotation symmetry. Yeah, so anyway, you can write down answers like this. Put in some two functions here. Okay? Put in some two functions here. So this is the most general solution, which is consistent with the translation symmetry in the t and x direction and the rotational symmetry in the t and x directions. Okay? And then you have just two functions which can only depend on z, because you cannot depend on t and x. Otherwise, you break translation symmetry. So this is the most general metric. You have two undetermined functions. Then you plug into Einstein equation, and then you solve it. Okay? So you find, in fact, h actually equal to 1 over g equal to something like this in d dimension. In d dimension, say if I have a ADSD plus 1, and then you find a very simple metric like this. So let me again give you a slight quiz. So why I don't put a function here? So why in principle, I can also put a function here, right? So why I only put the function here and the function here, but not put the function here? Yeah, exactly. Because you can imagine this just as a definition of z, okay? And then, but then I don't have freedom to choose this z. Or I can choose here to be 1, and then I need to put the function there. Okay. So in this metric, the horizon is at z equal to z0. Z0 is some constant. So z0 is some constant. Z0 is some constant. Right there, z0, and indeed have the topology of the d minus 1. Okay, look at the z equal to 0. The topology is this r. It's not the sphere. And also you see that when you go to infinity, the f and g approach 1 with a very fast fall off with d to the power d. So this is normalizable. Okay? And this is normalizable. So this behavior is normalizable. Okay? So this matrix satisfies all our criterions. And the standard black hole thermodynamics will ensure this is a thermodynamic system. Okay? So this must be dual to our finite temperature Yang-Mills theory. Okay? Okay, so now let's work out the temperature in terms of Z0. So just using the standard trick, going to the Euclidean signature. Which we have discussed before, and require the matrix is regular at the horizon. When you go to Euclidean signature, require the matrix is regular at the horizon, and then you can deduce that this should have some specific periodicity. Anyway, I hope you still remember that. So you can deduce the temperature of the black hole. So beta is equal to 4 pi equal to d times z0. Okay? So you can deduce. So this you remember, right? Okay, good. So emphasize. This is the temperature measured in T, because whenever, as we emphasized many times before, whenever you talk about temperature, you have to refer to a time unit to define the temperature. And this temperature is defined with respect to this time. Okay? So in other words, this is the boundary temperature. So in the bulk, of course, depending on the value of Z, the local temperature is different. And this is the temperature corresponding to the boundary. Okay? So this relation is, again, very interesting. So now, in the gravity side, so this is Z equal to 0 boundary. And now on the gravity side, now there's a horizon at Z equal to 0. Z equal to Z0. And this horizon, according to this formula, is proportional to 1 over T. It's proportional to 1 over T. Again, this is the reflection of the RUV connection. Because if you consider very high temperature means you are probing very high energy process. Okay? Then Z0 becomes small, then the horizon moves to the boundary. Okay? The horizon moves to the boundary. And when T becomes small, then Z0 becomes big, then the horizon moves down. Okay? So that means that depending on the value of T, you can probe different regions in the gravity side. So for very high temperature, you probe very tiny region near the infinity. And for a small T, then you can probe more and more regions. Okay? Again, this is a reflection of RUV. Any question on this? Now, with this black hole solution, we can work out all its thermodynamics. And then we should be able to work, then just by definition, essentially by definition, then for example, the black hole entropy should be, then it should be identified with the field theory entropy, or black hole free energy should be identified with the field theory free energy, etc. it just essentially if there's a relation, if black hole describe the field theory at finite temperature, then you should be able to equate their thermodynamic quantities. Okay? And this way, we can actually use the black hole thermodynamics now to calculate the thermodynamic behavior of a strongly coupled and for super Yang-Mills theory. Okay? So we can now obtain thermodynamic behavior, thermodynamic quantities at strong coupling in an equal super Yang-Mills theory in a black hole. Okay. So now let's do that. So now, now let's specify to d equal to 4. So that's corresponding to the 4-dimensional boundary. So let's do d equal to 4. So now let's first do the black hole entropy, which is the easiest thing to do. So the black hole entropy is just the area of the horizon divided by Newton constant. So we have to use the effective 5-dimensional Newton constant. So we work with ADS5. So with dimension reduction on the S5, so we work with the 5-dimensional Newton constant. And then the area here is just infinite volume. It's just dx1, dx2, dx3, because this is just parallel to the boundary, but doesn't matter. It doesn't matter. So so what this defines, or still times r cube to the z0 cube. Okay, because you have to multiply the area at the horizon. So you evaluate, so essentially compute the determinant of the spatial part at the horizon, evaluate at the z0. Okay, evaluate at the z0. So you have this factor, and then you have this infinite factor. But this infinite factor, it doesn't matter. We can just take it out. Then what you get is the entropy density. So then we find the entropy density. It's essentially just given by this r cube divided by z0 to the cube for g5. Okay? So now you can just plug in the numbers. So now you have to use this equation. G5 divided by r cube in n equal to is related to the n equal to super Yang-Mills related to pi divided by 2n squared. And then you plug in this relation to relate z0 to t. And then after a tiny bit algebra, so you find n squared t cube. Okay. Again, this answer makes sense. Again, you can do some very minimal consistency check. So first is that this is proportional to t cube. It makes sense because we are working with a 4-dimensional scale invariant theory. And entropy density, entropy by itself does not have a dimension. And entropy density should have dimension cube because of the volume. You divide it by the volume. Okay, should be 1 over volume. Do you follow? So entropy density should have dimension. Entropy density should have dimension m d minus 1. Okay, because the d minus 1 come from because you divided by entropy by the volume, and the volume have 1 over volume have dimension m d minus 1. Okay, and but here in the scale invariant, so you don't have any other scale factor. You only have t, so must come from t to the d minus 1, so you get t cube. Okay, and also this is proportional to n squared, and of course in the Lagrange Yang-Mills theory should be proportional to n squared. So now you can also obtain, say, for example, the energy density and the pressure, etc., by calculating the Tm mu. So you can calculate the, say, 1-point function of the stress tensor. Then you can read what is the energy density, and what is the pressure, etc. And so this is the same as what we did. It's very similar procedure as what we did before for the scalar field theory. The one-point function of the stress tensor is just, you can read it from the counterpart of the B modes, a counterpart of the normalizable modes. Okay? So here the normalizable mode is just this z to the power d, and the coefficient is 1 over 0, 1 over z0 to the power d. And so that tells you you should be proportional to 1 over z to the 0 to the 4. Okay? Okay? So because that's the analog of this B mode, the normalizable mode, to the 1 over z to the 0, 4. And again, this will be proportional to t to the power 4. Again, this is consistent on dimensional ground because the energy density have dimension m to the power d. And so it's t to the power 4. But to actually work out the prefactor requires a little bit effort. In the scalar case, we say it's 2 nu times b. So in the gravity case, in the metric case, it gets a little bit more complicated. Anyway, but you can read the scale. Okay, I will not calculate the prefactor using this method. So to calculate the prefactor is easier just to use the thermodynamics. So because S just equal to the free energy divided by T, now so now everything here should be considered as the density. So S is entropy density, and F is the free energy density, etc. So you can just, we know now the entropy. You can just integrate the free energy density. So this is equal to pi squared divided by 8 n squared t to the 4. Okay? And then you can find out the energy density, F plus Ts. So you find it's 3 pi squared by n squared to the power 4. Okay. So this, if you work out the one-point function of the stress tensor carefully of the prefactor, you will find this. Okay. So these are the results at lambda equal to infinity. So these are the strong coupling results. All these are the strong coupling results. Okay. So the thermodynamical behavior.
No, F. How to get F?
No, you just integrate this equation.
Okay.
Yeah, just integrate that equation. So this is the behavior at the infinite lambda. So now let's compare with the free theory. Okay. So this is undergraduate thermodynamics. So let's just calculate the entropy density with zero coupling. So I have to remind you one thing, is that in the each massless bosonic degree freedom contribute to the entropy density 2 pi squared divided by 45 to the power t cubed. I don't know whether you still remember this thing. So in 4 dimensions, a single massless degree freedom contribute to the entropy density. This comes from doing the single massless bosonic degree freedom contribute to the entropy like this. Okay. This is a good thing to remember. And now in the n-4 super Yang-Mills theory, we have 8 boson. We said before we have 8 massless boson degree freedom, and we have 8 fermionic massless degree freedom. And each fermionic degree freedom contributes to how much of the boson? Do anybody know? a massless fermion compared to the massless boson, what is the ratio for each degrees freedom contributed to the entropy density in the free series, free particle? No. No, 7/8. Okay. And now in the SUN gauge theory, we have n squared minus 1. We have n squared minus 1 in the joint representation. So now you can calculate this is a result of free series. So let's take large n, forget about the 1. So then you get 2 pi over 3, 2/3 pi squared n squared t to the power cube. So now you find something remarkable. Now you find something remarkable. You find s lambda equal to infinity divided by s lambda equal to 0 is equal to 1/2 divided by 2/3. So it becomes 3/4. So you go from 0 coupling to infinite coupling, and the entropy density changed by 3/4. Okay. So there's a long story. There are several long stories I can tell. A good story I can tell about this thing, but now I run out of time. But now let me mention a couple of words on your p-side problem. So in the p-side problem, you want to compute this Wilson loop, the same Wilson loop, the L and the T at the finite temperature. So now instead of the pure ADS, you use this black hole geometry. You use this black hole geometry. Okay? Use this black hole geometry. So what you will find, so physical expectation, physically, the VL, so you expect the potential between the quarks and anti-quark will go to 0 when L is large. Okay? So physically, for this reason, so here, this thing, the same thing happens even in the QED. So this is just the story of the screening. Suppose you have electron and anti-electron, so of course they have interaction between them. But now if you have a plasma between them, you have many positive and negative charged particles can running around, and then their interaction will be screened. Okay? The interaction will be screened because there will be slightly more negative particle here and slightly more positive particle here, then they will be screened. Similarly, if you have a quark and an anti-quark, which is their colored object, and when you put them in the finite temperature, in the finite temperature you can excite many other massless colored degrees freedom. Then they're running around those quark and anti-quark, then they will screen them. So when they take the distance sufficiently large, then you will find the potential between them goes 0. Okay. So on the gravity side, what you will see. So on the gravity side, what you will see. So now you cannot do everything analytically, but you can derive the qualitative behavior analytically. It said if the L is small, so suppose here is the horizon. When the L is small, then of course you just connect the string with close by. Nothing changes. Nothing much changes from our 0 temperature calculation. And this makes sense because at short distance you probe the UV physics. And to probe the UV physics, of course, you don't see the temperature. So for L, it's much, much smaller than 1 over temperature. Then you don't see the effect of the temperature, and the result will be just like small corrections to the vacuum result. But now when L becomes of order 1 over the temperature, then you find something interesting happens. Then the L, then this worksheet will roughly go to the horizon. Then what we will find in the end, when the L becomes, say, larger than some value, say, of order 1 over t, you find this, the only solution you can find is that this string just 2 string hanging down. That's the only solution. And then that means that the quark and the quark no longer interact with each other. Okay? And then they're screened. So short distance is the same as in the vacuum, but when you go to long distance, they of order 1 over temperature, and then eventually they will get screened. So, so this is a rather cute calculus problem, which I'm sure you will enjoy. Yeah, that's all for today.